In 1994, a comet broke apart above Jupiter and sent 21 fragments crashing into the planet over several days. The largest struck with the force of roughly 6 million megatons of TNT, 600 times the combined explosive power of every nuclear weapon on Earth. Jupiter barely noticed. Within weeks, the atmosphere had closed over the impact scars, leaving almost no trace that anything had happened. And that is the first strange thing about Jupiter. It is not simply enormous, it is 1,300 times the volume of Earth, with enough space to swallow every other planet in the solar system and still leave room. There is no surface, no ground, no place where a spacecraft could land and simply sit. The deeper you descend, the more the planet transforms. Hydrogen is compressed until it behaves like a liquid metal, conducting electricity and generating a magnetic field vastly more powerful than Earth's. The radiation surrounding Jupiter is so intense that an unprotected human would receive a lethal dose within hours. And beneath all of that, somewhere in the darkness, is Jupiter's interior. No spacecraft has ever reached it. No instrument has directly observed it. Even now, scientists are still debating what its deepest layers actually contain. Then there is the Great Red Spot, a storm larger than Earth that has raged for centuries, and the moon Io, where Jupiter's gravity is constantly stretching the world until volcanoes erupt across its surface. Jupiter has been influencing the solar system since long before humanity existed. It may have even helped determine whether Earth became a habitable world at all. What is actually happening beneath those clouds? What does hydrogen become when pressure reaches levels impossible to reproduce naturally on Earth? And what could be hiding at the center of the largest planet in our solar system? If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. It starts with the planet that absorbed one of the most violent impacts ever witnessed and simply carried on. Jupiter began taking shape before the young solar system had finished settling into anything resembling the arrangement we know today. Roughly 4.5 billion years ago, clouds of gas and dust circled the newborn sun, and Jupiter started gathering material in the colder regions beyond the frost line. Out there, water and other volatile compounds could freeze into solid particles. Ice added considerably more building material than was available in the warmer inner solar system. Jupiter grew rapidly, pulling surrounding matter toward itself with increasing strength as its mass accumulated. The process accelerated. Once Jupiter became massive enough, its gravity began dominating the movement of nearby material, clearing and scattering objects across an enormous region. The planet eventually reached more than twice the combined mass of every other planet in the solar system. That number alone changes how we should picture it. Jupiter is roughly 86,900 miles across. By volume, more than 1,300 Earths could fit inside it. Yet despite that enormous size, Jupiter is surprisingly light for something so large. Its average density is only slightly greater than that of water. This is where the familiar phrase gas giant begins to become misleading. The word gas suggests something diffuse, something that could simply spread away into space. Jupiter does begin with hydrogen and helium, but gravity has compressed those materials under pressures that increase continuously with depth. Far below the visible atmosphere, ordinary distinctions between gases, liquids, and solids begin to lose their meaning. Even Jupiter's position in the solar system reflects its immense influence. The planet travels around the Sun at an average distance of about 484 million miles, requiring almost 12 Earth years to complete one orbit. Its rotation is another matter entirely. Jupiter turns once in less than 10 hours, making its day shorter than that of any other planet. At the equator, the atmosphere races around the planet, while regions at different latitudes move at different speeds. That rapid rotation stretches atmospheric circulation into enormous bands and helps maintain the powerful jet streams that define Jupiter's visible appearance. Yet the most revealing number may be its density. Imagine taking the entire planet and somehow compressing its immense volume into a single average. You would find material only modestly denser than water. Earth, by comparison, is several times denser. That difference tells us something fundamental about where Jupiter's mass resides. Earth concentrates most of its weight into a rocky interior beneath a relatively thin atmosphere. Jupiter has no comparable arrangement. Its enormous volume is dominated by hydrogen and helium, compressed progressively deeper by the weight of everything above. As we move inward, pressure becomes the dominant architect, reshaping the same elements that began as part of a young cloud surrounding the Sun. Jupiter's size is therefore only the first indication of what makes it extraordinary. The real transformation happens beneath it, where gravity takes familiar matter and forces it into conditions nature rarely creates. There is no line on Jupiter where you can say the atmosphere begins. As you descend, the surrounding gas simply becomes denser, hotter, and increasingly difficult to distinguish from a liquid. At the highest visible clouds, temperatures hover near minus 220 degrees Fahrenheit. Ammonia freezes there into crystals, helping create the pale bands we see from Earth. Above and between them, hydrogen and helium dominate, with smaller traces of methane, ammonia, hydrogen sulfide, and water. Those familiar stripes are the upper edges of enormous atmospheric currents. Each band can stretch thousands of miles across the planet, while Jupiter's rapid rotation organizes them into opposing streams. Along their boundaries, winds can differ by hundreds of miles per hour, creating immense shear zones that remain locked around the planet. As you descend, the temperature changes quickly. Within roughly 60 miles, it can rise beyond the freezing point of water. Another 60 miles deeper, temperatures can exceed 300 degrees Fahrenheit. The same atmosphere that began as an icy cloud layer is becoming something radically different. Then there is the lightning. Jupiter produces electrical flashes throughout its atmosphere, with powerful strikes occurring several times each second across the planet. The deepest lightning forms around the water cloud layer, where convection carries warm material upward and colder material downward. The result is an electrical environment unlike anything we experience on Earth. In 2020, the Juno spacecraft detected another form of discharge. These flashes appeared higher in the atmosphere, inside mixtures of ammonia and water. Scientists called them shallow lightning because they occur above the main water cloud region. The discovery mattered because ammonia can remain liquid under conditions where water would normally freeze. Mixed together, the two substances can form slushy droplets that transport electrical charge through the upper atmosphere. Jupiter had effectively revealed a second pathway for lightning, one that earlier models had not anticipated. We can trace this changing environment through the brief descent of the Galileo atmospheric probe. On December 7th, 1995, it entered Jupiter's clouds and transmitted measurements as it fell deeper. For 58 minutes, instruments recorded temperature, pressure, wind, and atmospheric composition. The probe encountered wind speeds that continued increasing with depth, reaching hundreds of miles per hour. Its measurements also revealed unexpectedly low amounts of water and helium. Then the transmission stopped. By that point, pressure had become strong enough to crush the probe's structure and destroy its instruments. Galileo had traveled only about 124 miles downward, yet that shallow passage revealed how rapidly Jupiter's atmosphere transforms with depth. What looks from Earth like a smooth collection of colored bands, is therefore a vast moving atmosphere, changing continuously in temperature, pressure, chemistry, and electrical behavior. Every layer is part of the same descent, and the deeper we go, the less familiar the rules become. For centuries, astronomers have watched one feature drift across Jupiter, changing shape while refusing to disappear. The Great Red Spot entered the historical record in its modern form in 1831, although Giovanni Cassini described a large oval on Jupiter as early as 1665. Whether those observations belong to the same storm remains uncertain, leaving its true age unresolved. What we can measure today is already extraordinary. The Great Red Spot stretches roughly 10,000 miles across, still broader than Earth, yet its dimensions have changed dramatically. During the 19th century, estimates placed it near 25,000 miles wide. Modern observations show a much smaller vortex, and its contraction has become one of the most closely followed changes in Jupiter's atmosphere. Even its outline shifts from year to year, with edges that fold, stretch, and sometimes form smaller disturbances along the perimeter. Look closely at its motion, and another distinction appears. The Great Red Spot rotates counterclockwise as an anticyclone, meaning its circulation moves around a region of higher atmospheric pressure. Its outer winds can reach roughly 425 miles per hour, while the entire vortex completes a rotation in about 4.5 Earth days. That circulation is sustained far from any solid ground. Warm material rises through the surrounding atmosphere, while the storm's enormous structure remains embedded within Jupiter's powerful jet streams. Smaller vortices sometimes approach the boundary and become stretched, absorbed, or redirected. Their interactions reveal that the spot is part of a larger atmospheric ecosystem rather than an isolated formation. Its color presents another mystery. The reddish appearance may develop when sunlight alters compounds containing ammonia and acetylene high above the main storm. These reactions can produce complex organic molecules called tholins, which may contribute to the coloration. Laboratory work supports parts of this explanation, yet the exact chemistry responsible for the Great Red Spot's particular shade remains unsettled. The storm also reaches downward. Measurements from the Juno spacecraft indicate that the vortex extends roughly 200 miles beneath the visible cloud tops. That depth places its circulation far below the region illuminated by sunlight, allowing the storm to interact with atmospheric layers whose behavior is governed increasingly by internal heat. Over time, other storms have become part of its history. In 2000, three white oval storms merged into one larger system that eventually developed a reddish color. Astronomers began calling it Red Spot Junior. Events like that show how Jupiter's atmosphere can reorganize itself over years and decades. A vortex can absorb another, stretch under pressure, or change its appearance while continuing to circulate across the planet. We are watching a structure whose lifetime exceeds generations, yet whose shape is never truly fixed. On a December morning in 1995, a small instrument entered Jupiter, carrying no hope of returning. The Galileo atmospheric probe had separated from its parent spacecraft months earlier, then approached the planet on a trajectory designed for one purpose: descend into an atmosphere no human machine had previously sampled directly. It arrived at roughly 106,000 miles per hour. Friction against the atmosphere drove the probe's heat shield to temperatures near 28,000 degrees Fahrenheit, briefly exposing its protective surface to heat comparable to the outer layers of the sundae. Within minutes, atmospheric drag had transformed that tremendous velocity into a controlled descent. A parachute opened. Instruments began measuring. The scientists waiting on Earth had expected a layered atmosphere, with ammonia ice above ammonium hydrosulfide and water clouds deeper down. Instead, the probe encountered the upper ammonia layer and found the deeper expected clouds largely missing at its entry location. That result mattered. Jupiter's atmosphere was proving less uniform than the models assumed. As Galileo continued downward, its instruments measured winds growing stronger with depth. Near the end of the descent, speeds reached roughly 450 miles per hour. Models had suggested that sunlight should drive much of the atmospheric circulation, making deeper winds weaker. The probe found the opposite. Water produced another surprise. Its measurements indicated roughly 1/10 of the water abundance predicted from the composition of the early solar system. Scientists could not immediately determine whether Galileo had entered an unusually dry region or whether their broader assumptions about Jupiter's composition needed revision. Helium offered another clue. The probe detected less helium than expected near the upper atmosphere, evidence consistent with helium separating from hydrogen and sinking deeper under Jupiter's immense pressure. Inside the planet, droplets of helium can descend through surrounding hydrogen, releasing energy as they fall. Galileo kept transmitting as conditions worsened. After 58 minutes, it had descended only about 124 miles from the cloud tops. Pressure had climbed to roughly 23 times the pressure at Earth's sea level, enough to overwhelm the probe's structure. Then the signal ended. Nothing survived the descent intact. Yet those final transmissions changed our understanding of Jupiter's atmosphere, revealing stronger winds, unexpected chemistry, and a vertical structure far more complicated than scientists had predicted. For you, the remarkable part is the distance Galileo actually traveled. 124 miles sounds enormous from Earth, but against Jupiter's full depth, it was only a thin beginning. The probe had barely entered the planet before pressure and heat erased the machine that had carried our instruments there. Its brief fall gave us something more valuable than survival: direct measurements from a place no telescope could reach. Pressure in Jupiter does something more profound than crush matter. It changes the rules governing matter itself. Beneath the region reached by Galileo, every additional mile downward adds the weight of an atmosphere already compressed above, and that weight becomes enormous. On Earth, pressure is familiar because our atmosphere is comparatively thin. At sea level, the pressure surrounding you is roughly 1 atmosphere. Deep inside the Mariana Trench, it rises to about 1,086 atmospheres. Jupiter passes that threshold far above the depths where any ocean on Earth exists. Only a few dozen miles beyond Galileo's final measurements, conditions become dramatically more severe. At roughly 600 miles beneath the cloud tops, pressure can approach 100,000 atmospheres. That is enough to crush ordinary structures instantly, while also forcing atoms into increasingly crowded arrangements. Consider diamond. On Earth, forming diamond naturally requires pressures of roughly 50,000 to 70,000 atmospheres, along with suitable temperatures and chemistry. Jupiter reaches comparable pressures hundreds of miles below its clouds, then continues climbing. At around 13,000 miles down, pressure may reach roughly 3 million atmospheres. At those depths, imagining Jupiter as simply a deeper atmosphere stops being useful. The hydrogen surrounding us is being compressed into a dense state where its familiar behavior begins to disappear. Even materials chosen for extreme strength would eventually fail. Titanium and tungsten can withstand tremendous forces in engineered environments, while diamond is among the hardest natural materials known. None can preserve its ordinary structure under Jupiter's deeper conditions. The reason lies at the atomic scale. As pressure rises, atoms are pushed closer together until the electron clouds surrounding them begin to overlap. Chemical bonds become distorted, weakened, and eventually rearranged. The distinction between separate molecules becomes increasingly difficult to maintain. This transformation happens gradually. There is no single depth where everything suddenly changes. Instead, increasing pressure continuously alters density, temperature, electrical behavior, and the way particles interact. For you, the strange part is that Jupiter does not need an exotic substance to produce these effects. It begins with hydrogen, the simplest and most abundant element in the universe. Gravity alone provides the force. Nothing else is required to begin this transformation. As we descend farther, hydrogen becomes so compressed that its electrons can no longer remain confined to individual atoms. They begin moving through the surrounding material, producing electrical conductivity on a scale ordinary gases cannot achieve. The pressure, therefore, becomes more than a destructive force. It becomes an architect, reorganizing familiar matter into states that cannot exist naturally at Earth's surface. Far below the clouds, Jupiter is transforming the simplest substance we know into something with properties radically different from the gas that entered its atmosphere. Deep inside Jupiter, hydrogen reaches a strange turning point. The substance that began as an ordinary gas becomes electrically conductive, dense, and fluid under pressures reaching several million times those found at Earth's surface. At roughly 13,000 miles beneath the cloud tops, pressures may reach between 1.4 and 3 million atmospheres. Hydrogen atoms are forced so close together that their electrons can move freely through the surrounding material. Instead of remaining attached to individual atoms, those electrons behave more like the mobile electrons inside ordinary metals. That transformation gives the material its name, metallic hydrogen. You would not find a shiny metal buried there. Metallic hydrogen is expected to exist as a dense fluid with electrical properties unlike ordinary hydrogen. The immense pressure changes how its electrons move, allowing the material to conduct electricity extremely efficiently. For decades, scientists could only predict this state from theory. Then laboratory experiments began pushing hydrogen toward the required conditions using diamond anvil cells, devices that squeeze microscopic samples between opposing diamond surfaces. Some experiments produced evidence consistent with metallic hydrogen under extreme compression. Maintaining the material after pressure was released proved far more difficult. Once the crushing force disappeared, the hydrogen returned toward its familiar molecular state. Jupiter has no such escape from pressure. Its enormous interior provides the conditions continuously, creating a metallic hydrogen region estimated to extend for roughly 25,000 miles. That layer contains a staggering volume of electrically conducting fluid, rotating along with the planet beneath its atmosphere. Rotation changes everything. As Jupiter spins once every 10 hours, the conductive interior moves through its own magnetic environment. Electric currents develop within the fluid, and those currents generate a magnetic field. This process is called a dynamo, meaning motion inside electrically conducting material creates and sustains magnetism. Earth has a dynamo too. Ours operates within moving molten iron deep beneath the surface. Jupiter uses a radically different material, with metallic hydrogen occupying a vast portion of its interior. The result reaches far beyond the planet itself. Jupiter's magnetic field pushes charged particles outward, creating a magnetosphere that stretches hundreds of millions of miles through space. Its shape changes with the solar wind, compressed on the sunward side and drawn into an enormous tail extending away from the sunday. We can detect the consequences from spacecraft and telescopes, even though the metallic layer itself remains inaccessible. Instruments measure magnetic fields, charged particles, radio emissions, and gravitational effects, allowing scientists to reconstruct what the interior might contain. There is something remarkable about that indirect view. We cannot place a detector inside metallic hydrogen, yet its electrical motion announces itself across space. The largest planetary magnetic field in our solar system, therefore, begins with something extraordinarily simple: hydrogen, compressed by gravity, rotating deep within Jupiter, becomes the moving conductor that powers an invisible structure extending far beyond the clouds. And beneath that conducting ocean, pressure continues to rise. A spacecraft can pass through Jupiter's neighborhood without touching anything and still be damaged by what it cannot see. Jupiter's magnetic field fills the surrounding space with charged particles, creating a radiation environment that has challenged spacecraft sent close to the planet. Near Jupiter, the magnetic field is roughly 20,000 times stronger than Earth's surface field. Its influence reaches hundreds of millions of miles outward, forming a magnetosphere shaped by the solar wind. Inside this enormous region, particles become trapped and accelerated. Electrons and protons race along magnetic field lines, forming radiation belts far more intense than Earth's Van Allen belts. A spacecraft entering these zones moves through energetic particles. The Galileo spacecraft experienced that environment for years. From 1995 to 2003, radiation gradually degraded its electronics. Europa sits inside this environment too. At a distance of roughly 417,000 miles from Jupiter, its icy surface receives intense radiation. An unprotected human there would receive a lethal dose in a matter of hours, making the surface one of the most hostile places we have explored in the solar system. Yet, Jupiter's radiation does more than threaten spacecraft. It creates one of the most powerful natural light displays known in our planetary system. Charged particles, guided toward Jupiter's poles, collide with the upper atmosphere, transferring energy to atoms and molecules. Those interactions produce auroras that can span regions larger than Earth itself. Some of Jupiter's auroral emissions occur at ultraviolet wavelengths, while others produce powerful X-rays. The X-ray auroras are partly generated by heavy ions originating far from Jupiter, then accelerated through its magnetic environment. The source of those ions is connected to Jupiter's moons. Io continuously releases volcanic material into space, where sunlight and energetic particles strip electrons from atoms and create plasma. That material becomes part of the magnetosphere and helps feed the enormous electrical system surrounding Jupiter. We can therefore trace a chain stretching across hundreds of thousands of miles. Volcanic eruptions on Io supply material. Jupiter's magnetic field captures it. Charged particles accelerate through the surrounding space, and some eventually strike the polar atmosphere. Juno was built with this environment in mind. Its computers sit inside a titanium radiation vault, surrounded by protective shielding, designed to reduce the particle exposure reaching sensitive electronics. Even with that protection, mission planners had to shape Juno's orbit carefully. The spacecraft dives close to Jupiter for science, then spends much of its orbit farther away, limiting the time it remains inside the most intense radiation regions. From Earth, none of this is visible with our eyes. There is no glowing boundary marking the magnetosphere, no surface revealing where the radiation begins. Yet its effects reach across space, shaping spacecraft operations, altering the behavior of moons, and producing auroras powerful enough to radiate energy far beyond anything generated by Earth's polar lights. Deep beneath Jupiter, another kind of weather may be falling through the planet itself. Helium, normally mixed with hydrogen, can separate under the extreme conditions of the deep interior and begin sinking through metallic hydrogen. The idea emerged during the 1970s when planetary scientists realized that helium might become less soluble as pressure and temperature increased. Instead of remaining evenly distributed, helium could gather into dense droplets. Gravity would then pull those droplets downward. The process resembles rain only in one basic sense. Material falls. The surrounding fluid offers resistance, so the descent is nothing like falling through air. Each droplet moves through a dense interior where pressure and heat continue changing with depth. There is no open atmosphere beneath the clouds. Helium droplets would descend through a dense, electrically conducting fluid, moving slowly through material compressed to extraordinary densities. As each droplet sinks, gravity converts its potential energy into heat. That energy matters on a planetary scale. Jupiter releases more heat than sunlight alone can provide. It radiates roughly 1.7 times the energy it receives from the sun, meaning some of its warmth comes from within. Helium rain is one important contributor to that internal energy, alongside the planet's slow gravitational contraction. We can trace evidence for this process through Jupiter's atmospheric composition. The Galileo probe found less helium near the upper atmosphere than scientists expected, suggesting that helium had been removed from those higher layers. That observation was significant because the missing helium had somewhere to go. Under greater pressure, separation becomes increasingly favorable, allowing helium to collect and descend into deeper regions. As the droplets continue downward, the story becomes more complicated. Models suggest they may eventually dissolve back into the surrounding hydrogen at greater depths, where rising temperatures change the conditions again. This creates a possible circulation cycle, with helium separating, sinking, dissolving, and becoming redistributed over immense spans of time. Imagine that cycle continuing for billions of years. Every droplet would be part of a planetary process, operating far beyond human timescales, moving through an interior we can never directly observe. Saturn appears to experience a related process. Its greater helium depletion and stronger excess heat have led scientists to suggest that helium separation may be even more advanced there. The comparison helps us understand that these giant planets are not simply enormous collections of gas. Their interiors evolve continuously. For you, the most unusual part may be where the rain occurs. Nothing falls through empty space. The droplets move downward inside a sea of metallic hydrogen, surrounded by matter already transformed by immense pressure. Jupiter, therefore, produces its own internal weather, far beneath the clouds we can see. There, gravity pulls helium through conducting hydrogen, releasing heat as the planet slowly rearranges itself from within. At the center of Jupiter, certainty begins to disappear. We can measure the planet's gravity from millions of miles away, yet the deepest region remains inaccessible to every instrument humans have built. For decades, scientists pictured a relatively compact core made from heavy elements, perhaps 10 to 15 times Earth's mass. Rock and ice would sit at the center, buried beneath the immense envelope of metallic hydrogen. Juno changed that picture. Between 2017 and 2022, measurements of Jupiter's gravitational field revealed subtle variations in how the planet pulls on passing spacecraft. Those variations suggested that the heavy material inside Jupiter is spread outward rather than concentrated into a sharply defined central body. Scientists call this a fuzzy core. Instead of ending at a distinct boundary, the core may occupy a vast region extending through roughly half of Jupiter's diameter. That diffuse structure could reach about 43,000 miles across, making it larger than several Earths placed side by side. One explanation begins during Jupiter's earliest history. A massive protoplanet may have struck the growing giant at extraordinary speed, mixing its heavy material deep into the young planet. Rather than remaining concentrated, those elements could have become distributed throughout the interior. The idea remains a hypothesis. Conditions near the center make direct investigation almost impossible. Pressure may reach between 70 million and 100 million atmospheres, while temperatures could climb from roughly 36,000 to 90,000 degrees Fahrenheit. At those temperatures and pressures, familiar categories lose their usefulness. Iron, silicon, and magnesium would no longer behave like the minerals we recognize on Earth. They would exist in extremely compressed, electrically active material mixed with hydrogen and helium. How do we know any of this? Gravity provides the strongest evidence. As Juno moves around Jupiter, tiny changes in its velocity reveal variations in the planet's internal mass distribution. Scientists can use those changes to reconstruct structures that cannot be seen directly. Seismology offers another possible path. Jupiter may experience internal oscillations, sometimes described as Jupiter quakes, that could carry information about deeper layers. Detecting and interpreting those signals remains difficult, especially inside a planet without a solid surface. Computer models then combine the measurements with known physics, testing which interior structures can reproduce what spacecraft observe. Different models can fit portions of the evidence, while disagreeing about the precise composition and boundaries of the deepest material. That uncertainty is important. We are not looking at a photograph of Jupiter's center, we are inferring it from gravitational fingerprints, atmospheric measurements, and physical models. The deeper we try to look, the more indirect the evidence becomes. Somewhere beneath thousands of miles of transformed hydrogen lies a region whose composition, structure, and history remain unresolved, hidden behind conditions that no spacecraft can survive. In March of 1993, three astronomers noticed something unusual moving across the night sky. Carolyn Shoemaker, Eugene Shoemaker, and David Levy had found a comet already torn into separate pieces by Jupiter's gravity. The comet was named Shoemaker-Levy 9. Its fractured appearance revealed what Jupiter's gravity could do long before the fragments reached the planet itself. Each piece followed a related trajectory, and calculations showed that the entire procession was headed toward Jupiter. For more than a year, astronomers knew the collision was coming. Nothing like it had ever been predicted with such advance warning. Telescopes around Earth were prepared, turning a distant planetary impact into an event watched almost in real time. Beginning on July 16, 1994, the fragments struck one after another over 6 days. The impacts occurred on Jupiter's far side, hidden briefly from observers on Earth, while the planet's rapid rotation carried each fresh scar into view. The largest fragment, called Fragment G, released an estimated 6 million megatons of energy measured as trinitrotoluene. For a brief moment, its impact produced a fireball brighter than the rest of Jupiter. Then the atmosphere began absorbing the disturbance. Dark impact scars spread through the upper clouds, some growing larger than Earth. They remained visible for months, leaving temporary marks on a planet whose atmosphere normally erases evidence of passing events. Shoemaker-Levy 9 gave scientists something rare. We could watch an entire planetary impact unfold from beginning to end, then compare the observations with calculations made before the collision occurred. The event also changed how we think about Jupiter's place in the solar system. Its enormous gravity can capture incoming objects, alter their trajectories, or send them away from the inner planets. That influence extends across a vast region of space. For Earth, the consequences are complicated. Jupiter can redirect objects toward the inner solar system as well as away from it, so calling the planet a simple cosmic shield would be an oversimplification. Yet, long term studies suggest its gravitational influence can substantially reduce the frequency of some large comet impacts reaching Earth. One estimate places that reduction near a factor of 1,000 over geological timescales. The exact effect depends on the population and orbital behavior of the objects involved. Jupiter continued demonstrating this role long after Shoemaker-Levy 9. In 2009, amateur astronomer Anthony Wesley detected another impact as a dark atmospheric scar. The feature spread across a region comparable in size to the Pacific Ocean. We rarely witness impacts on worlds beyond our own. Jupiter gives us a different opportunity. Its enormous atmosphere records collisions that would otherwise remain invisible, turning each encounter into evidence of the gravitational architecture surrounding Earth. Io does something no other large moon in the solar system can match. Its surface is continually renewed by volcanic eruptions, driven by gravitational forces that reach deep into the moon's interior. Orbiting roughly 262,000 miles from Jupiter, Io travels through an intense gravitational environment. Jupiter pulls strongly on the Moon, while Europa and Ganymede repeatedly influence its orbit. Their gravitational relationship keeps Io moving through a pattern of changing tidal forces. Those forces stretch and compress Io with every orbit. The process generates enormous internal heat, allowing molten rock to remain active beneath the surface. The result is a world covered in volcanoes. More than 400 active volcanic regions have been identified on Io. Some produce towering plumes, while others create enormous lava flows that spread across the surrounding landscape. Temperatures in some lava lakes can reach roughly 3,000 degrees Fahrenheit. Loki Patera is the largest known volcanic feature. Its lava lake spans approximately 126 miles across, making it larger than Lake Ontario. The surface periodically overturns as cooler material sinks and hotter lava rises from below. Another volcano, Pele, produces plumes rich in sulfur compounds. Some rise roughly 190 miles above Io's surface before falling back and spreading across the surrounding terrain. The colors we see from spacecraft come largely from sulfur and sulfur dioxide. Yellow, orange, white, and darker regions cover the moon in patterns that change as eruptions deposit fresh material. Io's volcanic activity also reaches beyond the moon itself. Every second, roughly 1 ton of sulfur dioxide escapes from the surface into space. Jupiter's magnetic field then captures much of this material, stripping electrons from atoms and turning the gas into electrically charged plasma. That plasma forms a torus around Jupiter along Io's orbital path. A torus is a ring-shaped structure with a hollow center, similar in geometry to a donut. Here, however, the ring is made from electrically charged particles originating from a volcanic moon. The system becomes a remarkable exchange. Io loses material, Jupiter's magnetic field captures it, and the resulting plasma races around the planet. Radio emissions emerge from this interaction. Scientists can detect signals from the Jovian system on Earth, allowing us to observe electrical activity generated hundreds of millions of miles away. The plasma also strengthens Jupiter's already intense radiation environment. Particles supplied by Io become trapped and accelerated within the planet's magnetosphere, linking the moon's volcanoes directly to conditions throughout the surrounding Jovian system. For you, the strange part is how far this connection extends. A volcano erupting on Io does more than reshape a distant moon. Its material becomes part of Jupiter's enormous electromagnetic environment, where it can influence particles, radiation, and radio emissions across space. Io is therefore being transformed by Jupiter while simultaneously feeding the system around it. Every eruption adds another contribution to that immense exchange, carrying fragments of the moon outward into the magnetic domain of the planet that continually pulls it apart. Europa gives us an unusual kind of landscape, one where the most important terrain lies beneath our feet. Its surface is a shell of water ice, fractured by long reddish-brown markings that cross the moon in sprawling patterns. These markings, called lineae, may contain salts and sulfur compounds transported upward from deeper layers. They offer scientists a possible connection between the frozen exterior and the hidden ocean below. That ocean is enormous. Beneath an ice shell estimated between 10 and 20 miles thick, Europa may contain a global body of liquid water reaching depths of roughly 40 to 100 miles. The total volume could exceed all of Earth's oceans combined. The water remains liquid through a continual exchange of gravitational energy. Jupiter stretches Europa as the moon follows its orbit, while neighboring moons help maintain the orbital arrangement that keeps this flexing active. Heat generated inside Europa can therefore persist beneath a surface where temperatures fall to roughly minus 260 degrees Fahrenheit. For us, the significance is chemical as much as physical. Liquid water alone does not establish habitability. Life also needs energy and useful chemical ingredients, and Europa may possess both. Far below the ice, the ocean floor could contain hydrothermal vents. On Earth, these structures release heat and chemically rich fluids from the seafloor, supporting ecosystems that obtain energy without sunlight. If similar environments exist beneath Europa, they could provide usable energy within an otherwise lightless ocean. We cannot yet say whether anything lives there. Europa's surface offers no direct answer. Even the possible water plumes remain difficult to confirm. Observations from the Hubble Space Telescope have identified features consistent with water vapor rising above the surface, particularly near the southern region. If such plumes are connected to the ocean, material from below could occasionally reach space. That possibility changes the scientific problem. Instead of drilling through miles of ice, future spacecraft may be able to study material that naturally escapes from Europa's interior. The Europa Clipper spacecraft is designed for this investigation. Launched in October 2024, it is expected to begin a series of close Europa flybys in 2030. Across dozens of encounters, its instruments will examine the ice shell, surface composition, magnetic environment, and possible plume activity. Each pass can add another piece to the puzzle. Gravity measurements can reveal how mass is distributed inside the moon, while magnetic observations can help determine whether a conductive ocean lies beneath the ice. Spectrometers will examine surface materials in detail, searching for compounds that may have moved upward through fractures. Radar instruments will also investigate the ice, probing structures hidden beneath the surface. Europa, therefore, gives us a rare scientific opportunity. Its exterior preserves clues from an environment we cannot directly reach, while its interior may contain an ocean larger than anything visible on the moon itself. The reddish fractures crossing the ice may be pathways through which chemistry from a hidden world becomes detectable from above. Ganymede changes the scale, of what we mean by a moon. With a diameter of 3,273 miles, it is larger than Mercury, making the familiar categories of planet and satellite feel less useful here. Its size is only part of the story. Ganymede possesses something no other moon in our solar system is known to have: its own internally generated magnetic field. Deep within the moon, moving electrically conductive material creates a miniature magnetosphere, a region where Ganymede's magnetic influence shapes charged particles around it. That field exists inside Jupiter's much larger magnetic environment, creating a complicated meeting of invisible boundaries. Magnetic field lines bend, reconnect, and interact as Ganymede travels through the surrounding plasma. For us, this gives the moon a rare identity. It is both a world under Jupiter's influence and a magnetized body with an influence of its own. Beneath the surface, another structure waits. Evidence indicates that Ganymede contains a vast subsurface ocean buried beneath layers of ice. The water may begin roughly 100 miles below the surface, while additional ice could separate the ocean from the deeper interior. The evidence came from an unexpected place. In 2015, observations from the Hubble Space Telescope examined Ganymede's auroras, glowing arcs produced when charged particles interact with its magnetic environment. Those auroras shifted in ways that revealed the presence of a large electrically conductive ocean beneath the surface. The ocean may contain more water than all of Earth's surface water combined, yet its structure differs from Europa's. Layers of high-pressure ice could isolate much of Ganymede's ocean from the rocky material below, potentially limiting the chemical exchange that makes some environments more favorable for life. That distinction matters. Water provides an essential ingredient, but chemistry determines what can happen within it. Ganymede may hold an immense reservoir while offering fewer pathways between water, minerals, and energy. Its surface preserves a much older history. Dark regions covered with ancient craters occupy parts of the moon, while brighter grooved terrain records periods of intense geological deformation. These grooves stretch across enormous areas, suggesting that Ganymede's crust was fractured and reshaped billions of years ago. The Galileo spacecraft visited Ganymede repeatedly, making 6 close passes between 1996 and 2000. Those encounters provided additional evidence that the hidden ocean is electrically conductive, consistent with dissolved salts carried through the water. A newer generation of exploration is approaching. The European Space Agency's Jupiter Icy Moons Explorer spacecraft launched in April 2023 and is scheduled to enter orbit around Ganymede in 2034. It will become the first spacecraft to orbit a moon beyond our own. When we picture a moon, we often imagine a smaller companion circling a planet. Ganymede refuses that simple picture. Beneath its ancient surface lies an ocean. Around it moves a magnetic field of its own, and within Jupiter's immense system, this moon behaves like a planetary world in miniature. Callisto carries its history openly. Across its dark surface, impact scars remain layered over one another, preserving events that most worlds have erased. For nearly the entire age of the solar system, this distant moon has changed remarkably little. It circles Jupiter at roughly 1.17 million miles, far beyond the strongest tidal interactions shaping the inner moons. Without sustained tidal flexing, Callisto avoided the intense volcanism and crustal recycling seen elsewhere. Its surface, therefore, became a geological archive. Every large collision carved another mark into the ice and rock, while the absence of widespread resurfacing allowed ancient structures to remain exposed. When we study those craters, we are looking across billions of years. without needing to reconstruct everything from fragments. Some of the oldest features are enormous. Valhalla, Callisto's largest known impact basin, stretches roughly 1,900 miles across. Its formation sent immense shock waves through the crust, producing rings that spread outward for hundreds of miles and remain visible today. The scale is difficult to place beside anything familiar. An impact capable of shaping a region that large would have released energy on a planetary scale, excavating material before gravity pulled the fractured surface back into a new arrangement. Yet Callisto's frozen appearance hides an unexpected possibility. Measurements made during the Galileo spacecraft's encounters with the Moon revealed changes in Jupiter's magnetic field consistent with a conductive layer beneath the surface. The simplest explanation is a buried ocean containing dissolved salts. That raises an unusual problem. Callisto receives far less tidal heating than its neighboring moons, so what keeps water liquid beneath such an ancient crust? Radioactive elements inside the rocky interior may provide part of the answer. Their gradual decay releases heat, allowing small amounts of internal warmth to persist over immense spans of time. On Earth, the same fundamental process contributes to the heat flowing from our interior, though the conditions inside Callisto are very different. Its orbital position also matters. Io, Europa, and Ganymede participate in a precise gravitational rhythm called orbital resonance, where their orbital periods remain locked in a repeating relationship. Callisto lies outside that chain, reducing the repeated gravitational flexing experienced by its neighbors. Because of this separation, its interior may have evolved at a slower pace. The surface stayed heavily cratered, while the deeper layers could still preserve liquid water beneath ancient ice. Callisto gives us a rare contrast within Jupiter's family. Its neighbors reveal worlds being reshaped by internal energy, while this outer moon preserves the marks of a much older era. Beneath that battered exterior, however, a hidden ocean may still endure, making Callisto both an archive of the early solar system and a world with geological processes continuing below its ancient surface. Jupiter looks familiar from a distance, yet Juno has shown us how deceptive that view can be. Since arriving at Jupiter on July 4th, 2016, the spacecraft has transformed our understanding of the planet through measurements designed to reach beneath its visible atmosphere. Its orbit carries Juno through a narrow corridor of discovery. At its closest, the spacecraft passes roughly 3,000 miles above the cloud tops, then swings outward toward nearly 5 million miles before returning. This elongated path limits the time spent inside Jupiter's most intense radiation belts while repeatedly bringing instruments close to the planet. One of those instruments works without relying on visible light. Juno's microwave radiometer detects microwave energy emerging from different depths, allowing scientists to examine layers hidden beneath the clouds. Instead of seeing only the atmosphere's upper patterns, we can trace temperatures, composition, and winds hundreds of miles downward. Those measurements revealed that Jupiter's famous bands extend much deeper than their appearance suggests. The alternating atmospheric zones reach roughly 1,900 miles below the visible cloud tops. Beneath that depth, the planet's interior rotates more like a single connected body, with the dramatic differences between latitudes largely disappearing. Why does that boundary exist? Scientists still do not have a complete explanation. The finding shows that Jupiter's visible weather is connected to deeper physical processes, while also revealing a distinct limit to how far those motions penetrate. At the poles, Juno found an entirely different arrangement. The familiar horizontal stripes vanish, replaced by enormous cyclones arranged in geometric patterns around each pole. Jupiter's northern pole contains a central cyclone surrounded by 8 others, each roughly 2,500 miles across. The southern pole is different. 5 surrounding cyclones encircle its central storm, creating a pattern that lacks the northern arrangement's symmetry. These structures have remained remarkably stable during Juno's observations, despite the immense winds and turbulent atmosphere surrounding them. Gravity measurements added another layer of information. Tiny variations in Juno's trajectory allowed scientists to map differences in Jupiter's gravitational field, including an asymmetry between the northern and southern hemispheres. Such measurements reveal how mass is distributed inside the planet without requiring a probe to descend through its interior. They also allow scientists to test models of Jupiter's hidden structure against observations gathered from thousands of miles above the clouds. Those comparisons have exposed details that older theories could not account for. For you, the important shift is simple. We are no longer limited to studying Jupiter's appearance. Juno lets us measure how its atmosphere moves, how its poles organize themselves, and how its hidden mass alters the path of a spacecraft. Each orbit, therefore, becomes a kind of experiment. The spacecraft approaches, measures, and departs, carrying information from regions no human instrument had previously examined so closely. The first clue to Jupiter's rings came from a spacecraft looking back toward the planet. In March 1979, Voyager 1 passed through the Jovian system and revealed a faint structure surrounding Jupiter that telescopes on Earth had struggled to detect. The discovery changed our picture of Jupiter. Its rings are extremely dark and diffuse, lacking the brilliant reflective quality associated with Saturn. Most of their material consists of fine dust, produced when meteorites strike the small moons orbiting close to Jupiter. 4 main components make up the system. A thick inner halo surrounds Jupiter, followed by the main ring, then 2 extremely faint outer structures called the Amalthea and Thebe gossamer rings. Each occupies a different region around the planet. The main ring stretches roughly 4,000 miles across, yet its vertical thickness is less than 20 miles. Seen from the side, it becomes an extraordinarily narrow plane of particles suspended around the planet. That thinness hides an active environment. Individual grains are constantly moving through Jupiter's magnetic surroundings, where electrical forces can influence their trajectories. Sunlight also pushes against the smallest particles, gradually altering their orbits. The gossamer rings reveal just how difficult this system is to observe. Their particles are so sparse that they were not clearly confirmed until the Galileo spacecraft photographed them from within Jupiter's system in 1996. Amalthea and Thebe help explain where some of this material comes from. Meteorite impacts strike their surfaces, ejecting dust into space. Some of that debris settles into orbital paths, joining particles already circling Jupiter. But the rings are continually losing material. Charged dust can experience electromagnetic drag and slowly spiral inward, while solar radiation pressure can shift smaller particles outward. Individual grains therefore have limited lifetimes compared with the age of Jupiter itself. Something must keep replacing them. Meteorite impacts provide that renewal. Each collision can launch fresh material from the moons, adding new dust to the surrounding rings. The result is a system that behaves less like a permanent structure and more like an ongoing exchange between destruction and replenishment. This makes Jupiter's rings fundamentally different from the great rings of Saturn. Their appearance is subtle because their particles are dark, sparse, and constantly redistributed. They do not dominate the planet's silhouette. Instead, They remain embedded within Jupiter's larger gravitational and magnetic environment, where dust is shaped by impacts, radiation, and electromagnetic forces. When we look toward Jupiter, most of this structure disappears against the planet's brilliance. From inside the system, however, the rings become evidence of continual change. Every particle has a source, every orbit can evolve, and every impact can add something new. What Voyager 1 discovered in 1979 was therefore more than a faint band around Jupiter. It was a delicate record of collisions and forces operating together in the space surrounding the largest planet in our solar system. At Jupiter's poles, geometry emerges from turbulence. Juno revealed storms arranged with a precision that seems almost deliberate, even though each cyclone is an enormous rotating mass of gas. At the North Pole, one central cyclone is surrounded by 8 others. Each stretches roughly 2,500 miles across, with winds reaching 220 miles per hour. Together, they form an 8-sided pattern, unlike any persistent storm arrangement known on Earth. What makes the pattern remarkable is its endurance. Since Juno began observing Jupiter in 2016, the surrounding cyclones have shifted and pulsed without losing their positions. They can expand, contract, and change brightness, yet the overall arrangement remains intact. Earth offers little comparison. Our strongest atmospheric systems travel across oceans, interact with neighboring storms, and eventually weaken. Jupiter's polar vortices behave differently. Their rotation keeps them organized around the pole, while the surrounding atmosphere continually supplies energy through rising and sinking currents. Fluid dynamics makes this especially interesting. When researchers model rotating atmospheres, neighboring vortices tend to drift together and merge. Given enough time, several storms should become fewer, larger storms. Jupiter refuses that simple outcome. One possible explanation involves moist convection, the movement of warm, vapor-rich gas rising through deeper atmospheric layers. As this material rises and cools, it can release energy that strengthens individual vortices and helps maintain their separation. The storms also interact through narrow boundaries between them. These regions contain powerful jets flowing in opposite directions, creating barriers that can prevent neighboring cyclones from moving directly into one another. The result is a balance between attraction, rotation, convection, and atmospheric shear. Juno has also found that the poles differ strongly from Jupiter's familiar equatorial appearance. There, broad bands dominate the planet. Near the poles, immense vortices fill the view, revealing atmospheric behavior that becomes increasingly complex as we examine it more closely. The southern pole presents another variation. Its central cyclone is surrounded by 5 major circumpolar storms rather than 8, producing a different arrangement despite operating within the same planet. Why should 2 poles behave differently? The answer may lie deeper than the visible cloud tops. Infrared observations show that the polar cyclones release heat differently from nearby regions, suggesting that their atmospheric circulation reaches far beneath the layers we can directly observe. Those deep connections matter because Jupiter's weather is powered by energy moving through a vast interior. Heat rises, material descends, and rotation organizes the flow into structures that can persist for years. Saturn provides a useful contrast. Its north pole contains a single, enormous vortex shaped by a persistent wave pattern, rather than Jupiter's collection of separate cyclones. On Jupiter, stability comes through multiplicity. 8 storms hold their places around one, while another arrangement governs the opposite pole. We are watching a form of atmospheric order, created inside an environment that never stops moving, where immense clouds can maintain their geometry without ever becoming still. Earth did not form in isolation. Its orbit, its neighbors, and even the material that became its oceans were shaped within a crowded young solar system. Jupiter was already gathering enormous mass, while the planets were still assembling. Its growing gravity reached across millions of miles, disturbing smaller bodies that might otherwise have followed calmer paths. The asteroid belt became a region of competing trajectories, where repeated gravitational encounters prevented much of its material from joining into one large world. That influence extended farther inward. Water-rich asteroids and icy bodies from colder regions could be nudged onto new orbits, sometimes carrying volatile material toward the warmer inner planets. For you, the oceans beneath the night sky may therefore represent more than Earth alone. Their history could be connected to gravitational interactions involving a planet that formed much farther from the Sunday. The exact contribution remains debated. Scientists have found evidence that Earth's water came from several sources, including water-bearing rocky material incorporated during planetary formation. Jupiter's gravity may have helped deliver some of those ingredients, but the amount remains uncertain. Computer simulations reveal why the distinction matters. When researchers model planetary systems without a Jupiter-sized planet in a comparable orbit, the resulting inner worlds can become substantially different. Their masses, spacing, and orbital paths shift as countless smaller bodies interact over millions of years. One influential idea is called the Grand Tack hypothesis. In this model, young Jupiter moved inward through the developing solar system before changing direction and migrating outward. Its gravitational passage could have scattered planet-building material, clearing portions of the inner system while concentrating other material closer to the Sunday. Mars may preserve one consequence of that process. The planet is far smaller than many early formation models naturally produce, and Jupiter's migration could have removed much of the material that might otherwise have helped Mars grow larger. Yet the story becomes more complicated when we consider the asteroid belt itself. Its present population contains objects formed across different regions, including bodies rich in water and other volatile compounds. Jupiter's movements could have mixed these populations, leaving behind a belt that records the early rearrangement of the planetary system. We can even trace the effect through orbital architecture. Earth occupies a stable region where temperatures eventually allowed liquid water to persist, while Venus became far hotter and Mars much smaller. Those outcomes depended on many factors, but Jupiter was one of the largest gravitational influences nearby. So, when you look at Earth's place among the planets, the arrangement is more than a simple sequence of worlds. Jupiter helped shape the pathways through which matter moved, collided, scattered, and accumulated. Our planet may therefore carry a history written partly by a world that never approached it. Its oceans, its neighbors, and its position could all reflect gravity acting across immense distances during the earliest chapter of the solar system. The young solar system was a place of movement. Gas, dust, and growing planets surrounded the newborn sun, while gravity continually changed their paths. Jupiter may have traveled farther than we usually imagine. The Grand Tack hypothesis describes a remarkable migration. Proposed in 2011 by Kevin Walsh and his colleagues, it suggests Jupiter formed beyond the region where water could easily remain vaporized, then began drifting inward through the surrounding disk. As Jupiter moved, its enormous gravity disturbed the material around it. Rocky fragments were scattered, compressed, or redirected, changing the supply available to the developing inner planets. Earth, Venus, and Mars were still assembling during this period, so their eventual sizes depended partly on where this material ended up. Jupiter may have reached a position roughly 1.5 astronomical units from the Sun, placing it near the region now occupied by Mars. Then Saturn entered the story. As Saturn grew, gravitational interactions between the two planets changed their orbital relationship. Eventually, they became locked in a resonance, meaning their orbital periods fell into a repeating mathematical pattern. That interaction reversed Jupiter's inward movement. The direction changed. Jupiter began moving outward again. In the grand tack model, this reversal resembles a sailboat changing course, which gives the hypothesis its name. During the outward migration, Jupiter scattered material from colder regions toward the inner solar system, including bodies carrying water and other volatile compounds. That movement could explain several features that otherwise require separate pieces of history. Mars is much smaller than Earth, and the grand tack model gives Jupiter a way to remove much of the material Mars might have gathered. The asteroid belt is also far less massive than many simple formation models predict. Its present population adds another clue. The belt contains rocky bodies with different compositions, suggesting material from distant regions became mixed during the early rearrangement of the planets. Earth's position may also reflect this migration. As Jupiter and Saturn moved, the distribution of planet-building material changed across the inner system. Some regions were depleted, while others received new material, altering how quickly growing worlds could accumulate mass. Still, the grand tack remains a hypothesis. Other models can reproduce parts of the solar system's architecture without requiring Jupiter to travel so far inward. Scientists compare these models against planetary masses, orbital patterns, asteroid compositions, and the history recorded by meteorites. What makes the idea compelling is its ability to connect many separate features. One migrating planet could influence the amount of material available to another, reshape the asteroid belt, and redirect volatile-rich bodies toward the inner worlds. We often picture planets as permanent fixtures, each occupying its assigned place. Early Jupiter may have been something very different, a moving gravitational force whose changing path helped determine where the planets could grow. If Jupiter vanished today, the change would begin with gravity itself. There would be no explosion, no expanding shockwave, and no visible disturbance racing across the sky. Instead, countless objects would gradually begin following different paths through the solar system. The first losses would occur among the Trojan asteroids, which share Jupiter's orbital journey in two enormous groups. One group travels ahead of Jupiter, while the other follows behind, each held near stable gravitational regions roughly 60 degrees from the planet. More than 12,000 of these objects are currently known. Without Jupiter, those gravitational anchors would disappear. The Trojans would continue moving around the Sun, but their carefully maintained arrangement would unravel. Some would remain on distant solar orbits, while others could eventually encounter Saturn or other planets and receive new gravitational nudges. The asteroid belt would undergo a slower transformation. Jupiter currently dominates the gravitational environment around this broad population of rocky bodies, shaping their orbital gaps and limiting how easily material can gather into larger worlds. Remove that influence, and the belt would become dynamically different. Collisions could become more frequent over immense spans of time. Fragments would be scattered into new orbits, with some potentially crossing the paths of the inner planets. Earth would not suddenly face a storm of asteroids. The change would unfold gradually, across millions of years. Our planet's immediate orbit would remain remarkably stable. Jupiter is distant enough that its direct gravitational pull on Earth is relatively small compared with the influence of the Sunday. For you, the familiar length of the year would therefore continue almost unchanged at first. The outer planets would tell a different story. Saturn, Uranus, and Neptune are locked into a complicated gravitational arrangement, with each planet continually responding to the others. Jupiter carries the greatest mass among them, so removing it would alter the balance governing those distant orbits. Saturn would respond first. Its orbital path would adjust, which could then influence Uranus and Neptune through a chain of gravitational interactions. Over extremely long periods, small changes could accumulate into substantially different orbital configurations. Beyond Neptune, the Kuiper Belt would also feel the loss. Its distant icy objects occupy a region shaped by the gravitational history of the giant planets, and Jupiter's disappearance would remove one major participant from that long-term architecture. Earth's deeper history could change as well. Some planetary simulations suggest that Jupiter's presence has helped maintain the broad stability of the inner solar system over billions of years. Without that influence, the probability of orbital changes and increased impacts could rise over geological timescales. Yet there is an important uncertainty. Jupiter's role is complicated because the same gravity that can redirect dangerous objects can also destabilize them and send them elsewhere. So Jupiter is neither simply a shield nor a threat. It is part of the gravitational system that determines where material travels. If you removed it, the solar system would continue orbiting the Sunday. The planets would still shine, seasons would still change, and Earth would remain recognizable. But beneath that familiar appearance, the architecture would slowly begin to evolve into something different, shaped by the absence of the largest gravitational influence among the planets. Jupiter is still changing, even though its transformation unfolds across timescales far beyond a human lifetime. Deep inside, the planet continues to contract under its own immense gravity, converting gravitational energy into heat as its interior slowly becomes more compressed. That process has continued since Jupiter formed. The planet still retains energy from its birth, when enormous amounts of material collapsed together during the early solar system. As Jupiter gradually contracts, some of that stored gravitational energy is released as thermal energy. The effect is measurable. Jupiter radiates more energy into space than it receives from the Sunday. Helium rain contributes to this excess, while slow gravitational contraction provides another source. Together, these processes allow Jupiter to remain an active world long after its formation. For now, the planet exists in a relatively stable phase. Its internal heat will gradually diminish, its atmosphere will continue evolving, and its immense storms will draw from energy moving through deeper layers. But the Sun has its own future. In roughly 5 billion years, the Sun is expected to exhaust the hydrogen available in its core and expand into a red giant. Mercury and Venus are expected to be engulfed, while Earth's fate remains uncertain because of changing solar conditions and orbital effects. Jupiter lies far enough away to avoid being swallowed by the expanding Sunday. Its upper atmosphere, however, would receive dramatically greater solar energy as the Sun grows brighter and larger. The planet itself would remain bound to the solar system, although the Sun's changing mass would alter planetary orbits. Jupiter could gradually migrate outward as the Sun loses material through powerful stellar winds and later stages of its evolution. There is another possibility worth considering, one that belongs to physics rather than Jupiter's actual destiny. Jupiter is enormous, but it is still far too small to become a star. If it somehow acquired roughly 13 times its present mass, conditions in its interior could become sufficient for deuterium fusion, placing it in the category of brown dwarfs. A brown dwarf occupies an unusual middle ground. It can produce energy through limited nuclear fusion, yet it lacks enough mass to sustain the hydrogen fusion that powers ordinary stars. Jupiter falls far below even that threshold. To ignite sustained hydrogen fusion, an object generally needs roughly 80 times Jupiter's current mass. At that point, gravity would compress its interior until temperatures and pressures became sufficient to fuse hydrogen into helium. Jupiter would need an almost unimaginable amount of additional material. There is no natural process in the present solar system capable of supplying it. No wandering reservoir of gas is waiting to transform Jupiter into a second sun, and its orbit provides no mechanism for gathering such enormous mass. So Jupiter's future is fundamentally planetary. It will continue radiating its stored energy, gradually cooling as the solar system ages. Its storms may change. Its interior will slowly lose heat. Its surroundings will evolve with the sunday. Yet Jupiter will remain what gravity allowed it to become, an immense world that came close to the boundary between planets and stars, but never crossed it. In 1955, a strange signal began repeating across Bernard Burke and Kenneth Franklin's radio observations of the sky. They were mapping distant sources when the pattern returned with remarkable regularity. At first, the instrument seemed responsible. Then the source was traced to Jupiter. The discovery revealed a planet that could announce its presence across interplanetary space. Jupiter produces several families of radio emissions, each created by different populations of charged particles moving through its immense magnetic environment. The lowest frequency emissions include decametric radiation, the same broad class of signals Burke and Franklin encountered. These waves are closely connected to Io, whose volcanic material supplies charged particles to the region surrounding Jupiter. As those particles interact with Jupiter's magnetic field, electrons accelerate and generate radio waves that can travel across the solar system. Their strength is remarkable. Under suitable conditions, radio enthusiasts on Earth can detect some of these Jovian signals with relatively simple equipment. You can listen to a world millions of miles away without seeing it directly. Higher frequency emissions arise from electrons trapped within Jupiter's radiation belts. These particles can remain confined by magnetic field lines, circling the planet at tremendous energies. Their motion produces decimetric radiation, giving scientists another way to study the invisible environment surrounding Jupiter. Then came a remarkable transformation in 1979. During the Voyager 1 flyby, instruments recorded electromagnetic waves around Jupiter. Scientists could shift those measurements into frequencies audible to human hearing, turning patterns of electromagnetic activity into sound. The result was a sequence of crackles, pulses, and sweeping tones produced by processes far beyond ordinary experience. Nothing was physically making music in space. The sound emerged after scientific measurements were translated into a range our ears could perceive. Juno has continued this work since 2016, carrying an instrument designed to measure radio waves and plasma waves throughout Jupiter's magnetosphere. A magnetosphere is the region dominated by a planet's magnetic field, extending far beyond the visible atmosphere. These observations have revealed previously unknown wave patterns moving through that enormous region. Each pattern carries information about particles, magnetic fields, and energy transfer that cannot be seen through ordinary telescopes. Io remains part of this electromagnetic conversation. As its position changes during each orbit, Jupiter's radio emissions can change with it, linking volcanic activity to magnetic behavior across hundreds of thousands of miles. That connection gives Jupiter a remarkable physical voice. Its radio signals are evidence of particles accelerating, magnetic fields shifting, and moons exchanging energy with the planet. When we listen to those signals, we are hearing measurements transformed into sound, revealing activity that has always been unfolding beyond human sight. The signals also reveal how Jupiter's magnetosphere responds when its moons disturb the surrounding plasma. In that sense, the radio sky above Earth becomes another window into Jupiter's hidden machinery. On March 5, 1979, Voyager 1 reached Jupiter after crossing more than 1 billion miles of space. It passed within 174,000 miles of the cloud tops, close enough to reveal details that Earth-based telescopes could never resolve. For the first time, Jupiter filled a spacecraft camera with structure. Individual storms revealed layered edges, turbulent boundaries, and patterns moving through the atmosphere at vastly different depths. The familiar bands became active weather systems, changing across distances of only a few dozen miles. Then Io offered an unexpected discovery. During a navigation image, geologist Linda Morabito noticed something rising above the moon's edge. It resembled a small umbrella suspended above the surface. Further analysis showed that it was a volcanic plume, proving that active volcanism existed beyond Earth. The discovery changed Io immediately. Its surface was no longer interpreted as an ancient landscape preserved through time. Something was actively reshaping it. Voyager 1 also searched Jupiter for rings. The idea had become especially important after astronomers discovered rings around Uranus in 1977. When the spacecraft looked back toward Jupiter from an advantageous angle, a faint arc appeared around the planet. Jupiter had rings after all. They were difficult to see because their particles reflected very little sunlight. Voyager revealed that the giant planet possessed a subtle system of its own, hidden within the overwhelming brightness of Jupiter. 4 months later, Voyager 2 arrived. Its encounter became an unexpected demonstration of how rapidly worlds can change. Several volcanic regions on Io had already altered between the two visits. New eruptions had appeared, while previously observed features had weakened, shifted, or disappeared beneath fresh deposits. You could almost watch geology happening between two spacecraft encounters. The twin missions also transformed the Galilean moons from distant points of light into distinct worlds with different histories. Europa displayed an intricate network of surface fractures. Ganymede showed contrasting terrains shaped by ancient geological activity. Callisto preserved a heavily cratered record of impacts across immense stretches of time. Each moon revealed a different response to Jupiter's gravitational influence. Yet, the encounters were brief. Voyager 1 spent only a limited period near Jupiter before continuing outward towards Saturn and eventually beyond the planetary region. Voyager 2 followed a separate trajectory, using Jupiter's gravity to redirect its path toward the outer planets. Their importance continued long after the cameras stopped looking back. By 2024, Voyager 1 had traveled approximately 15.5 billion miles from the Sun, making it the most distant human-made object ever built. Its instruments were still returning information from interstellar space, decades after those first images transformed our understanding of Jupiter. The photographs themselves remain remarkable because they captured something more than distant scenery. They recorded a planetary system changing in real time, giving us our first detailed evidence that Jupiter and its moons were active, connected, and continually reshaped by forces extending across immense distances. For one remarkable year, two small spacecraft passed through that system, and Jupiter became a world we could finally begin to understand. The next generation of Jupiter exploration is already moving through space, carrying instruments designed to study worlds that earlier missions could only glimpse. The European Space Agency's Jupiter Icy Moons Explorer launched in April of 2023, beginning a long route toward the Jovian system. Its arrival is planned for July of 2031, after a sequence of gravity assists that will reshape its orbit and build the speed needed for the journey. Once there, the spacecraft will make repeated encounters with Europa, Ganymede, and Callisto before settling into orbit around Ganymede in 2034. That destination matters. Ganymede will become the first moon beyond Earth to receive a spacecraft in orbit. During its campaign, the mission will make 12 close passes of Ganymede, 21 of Callisto, and 2 of Europa, gathering measurements that can reveal how these icy worlds evolved. Radar instruments will probe beneath the surface, while magnetic measurements can help estimate the depth and electrical properties of hidden oceans. Spectrometers will examine surface materials and any compounds released from below. For us, these observations offer something unusual: indirect access to environments that no human instrument can simply touch, allowing chemistry and hidden water to be studied from a distance. Europa has another visitor on the way. NASA's Europa Clipper launched in October of 2024 and is scheduled to reach Jupiter in April of 2030. Its campaign will include 49 close flybys of Europa, with the spacecraft passing within 16 miles of the surface during its nearest approaches. A mass spectrometer aboard Europa Clipper can separate molecules by their mass, allowing scientists to identify chemical ingredients carried through the spacecraft's instruments. If plumes are active during those encounters, material rising from Europa's interior could provide samples of the hidden ocean without requiring a landing. Could a spacecraft detect chemistry associated with life? Scientists will be looking for amino acids and other organic molecules, while carefully distinguishing biological signatures from chemistry that can arise naturally. The distinction will matter because organic compounds can form through ordinary geological and chemical processes without biology. Elsewhere in the Jupiter system, another idea remains under consideration. The proposed Io volcano observer would focus on Io's intense volcanic activity, measuring changes in heat flow and studying how gravitational tides influence eruptions across the moon. Jupiter itself remains harder to enter deeply. The Galileo probe reached the atmosphere in 1995, but descending farther would demand materials capable of surviving extreme pressure, temperature, and turbulence. No approved mission currently plans to repeat that descent at greater depth. For now, Jupiter's deepest regions remain beyond direct exploration, while its moons offer the more accessible clues to the giant planet's complicated system. In 1976, Carl Sagan and Edwin Salpeter considered an unusual possibility. Could life exist without ever touching solid ground? Their paper imagined organisms drifting within Jupiter's atmosphere, occupying a narrow region where pressure and temperature might resemble conditions familiar on Earth. Far below the visible cloud tops, the atmosphere changes dramatically. At roughly 30 to 45 miles beneath the cloud tops, pressures may range from 1 to 10 atmospheres, while temperatures could span from about -10 to 150 degrees Fahrenheit. Those conditions fall within ranges tolerated by some of Earth's most resilient organisms. Sagan and Salpeter imagined three broad forms of atmospheric life. Sinkers would descend through the atmosphere, while floaters would remain suspended by producing gases lighter than their surroundings. Hunters would move between these populations, feeding on whatever biological material the deeper atmosphere could provide. The concept depends on chemistry already present around Jupiter. Hydrogen dominates the atmosphere, while carbon, nitrogen, oxygen, and sulfur compounds provide ingredients that could participate in complex reactions. Lightning supplies another important ingredient, energy, and Jupiter produces enormous electrical discharges throughout its atmosphere. Yet, the atmosphere presents a difficult environment for anything resembling life. There is no solid surface where an early biological system could simply establish itself. Vertical circulation constantly moves material through different temperatures and pressures, creating a continual problem for organisms that must remain within a narrow, habitable region. An organism drifting too high could encounter freezing conditions. Too low, and increasing pressure and temperature would become destructive. For Sagan and Salpeter's idea to work, atmospheric organisms would need extraordinary control over their buoyancy. A floater might function almost like a living balloon, regulating its position by producing or releasing gases as conditions changed. Speed would matter too. If circulation carried organisms out of favorable layers, reproduction would need to compensate for those losses. The population would therefore depend on a constant balance between growth, movement, consumption, and atmospheric escape. There is another difficulty. Jupiter's atmosphere is chemically active and repeatedly energized by lightning, radiation, and powerful circulation. Complex organic molecules may break apart before they can assemble into anything resembling a stable biological system. No spacecraft has detected evidence of life there. The hypothesis remains informed speculation, grounded in atmospheric physics and known chemistry rather than direct observation. Still, the idea raises a deeper question about where habitability can exist. On Earth, life is tied to land, oceans, and environments with accessible chemical gradients. Jupiter offers something stranger, a world where a hypothetical ecosystem would have to remain suspended within moving gas. We have not found such organisms. We also have not examined every relevant layer closely enough to declare the possibility impossible. Long before spacecraft crossed the darkness between worlds, Jupiter already belonged to human time. Its steady movement among the stars gave ancient observers a celestial marker, returning to nearly the same position every 12 years and becoming woven into calendars, omens, and systems of measurement. In Babylon, astronomers recorded Jupiter with remarkable care as early as 700 before the Common Era. They tracked its changing position against background stars, building tables that could predict where the planet would appear. Centuries later, clay tablets revealed something even more striking. Babylonian scholars used geometric procedures to calculate Jupiter's motion, including methods resembling the mathematical ideas of integral calculus. The discovery changed how we understand ancient astronomy and mathematical history. A tablet, now held by the British Museum, helped reveal this sophistication when researchers analyzed it in 2016. These observers were not merely describing what appeared overhead, they were turning the heavens into a computational record. They were transforming repeated observations into numerical predictions, extracting patterns from celestial motion with a sophistication that survived on clay. China developed its own relationship with the planet. Jupiter's 12-year cycle became a foundation for traditional calendrical systems, and its movement was associated with the 12 terrestrial branches used to organize time. The same 12-fold rhythm later became closely connected with the animals of the Chinese zodiac. For thousands of years, Jupiter remained a wandering light among familiar stars. Then, in January of 1610, the telescope changed what humanity could ask of it. Galileo Galilei turned his instrument toward Jupiter and found four tiny points of light nearby. Night after night, their positions changed. They were moons. That observation carried an implication far beyond Jupiter. If these bodies revolved around another world, then Earth could no longer be assumed to occupy the unique center of every celestial motion. The sky had become more complicated and therefore more interesting. Galileo's discovery gave physical evidence to a growing challenge against the geocentric model, the ancient idea that Earth stood at the center of the cosmos. Jupiter had become more than a bright planet. It had become evidence. The four moons were eventually known as the Galilean moons: Io, Europa, Ganymede, and Callisto. Their names came from Simon Marius, a German astronomer who independently reported observing them around the same period, adding another chapter to the story of who first saw what. When you look at Jupiter today, you are seeing the same planet that crossed Babylonian records and Chinese calendars. Yet the meaning of that light has changed repeatedly. We first treated Jupiter as a wandering sign. Then we measured it, mapped it, and discovered worlds circling it. The planet stayed in the sky. Our understanding moved. For all the knowledge Jupiter has given us, its deepest regions remain beyond direct observation. Every spacecraft has studied the planet from the outside, measuring gravity, magnetic fields, radiation, and atmospheric behavior, while the interior itself remains hidden beneath layers we cannot physically reach. We have never sampled the metallic hydrogen directly. No instrument has touched Jupiter's core. Even the amount of water throughout the atmosphere remains uncertain, because the Galileo probe entered a region that appears unusually dry, while later measurements from Juno have provided a broader but still incomplete picture. Some of the largest mysteries are written across Jupiter's poles. We can measure the cyclones, track their movements, and calculate their immense energies. Yet, we still cannot fully explain why the northern arrangement contains 8 surrounding vortices, while the southern pattern contains 5. Their persistence challenges our understanding of rotating atmospheres. Computer models can reproduce parts of the behavior, but reproducing the entire system remains difficult. Somewhere within those calculations, an important piece of Jupiter's physics is still missing. The same uncertainty reaches deeper. Juno's gravity measurements indicate that Jupiter may possess a diffuse core, where heavy elements are spread through a broad region instead of concentrated into a sharply defined center. We know the gravity field contains clues. We do not yet know exactly what those clues mean. Even the planet's atmosphere holds unresolved questions. The Great Red Spot has changed dramatically over recorded observations, yet the processes controlling its long-term energy remain uncertain. Is its present form temporary, or has the storm entered a new equilibrium? We can measure its changing dimensions, but its ultimate behavior remains difficult to predict. Beyond Jupiter itself, another unknown waits among the moons. Europa, Ganymede, and Callisto may contain substantial underground oceans, and each presents different chemical and physical conditions. We have evidence for water beneath their surfaces, but no direct chemical analysis has established whether biology exists there. That distinction matters. A potentially habitable environment is not evidence of life. Jupiter has been studied systematically for more than 4 centuries. 9 spacecraft have traveled through its system or examined the planet at close range, each one adding another layer to our understanding. Yet, every answer has revealed another boundary. We have learned how Jupiter rotates, how its atmosphere moves, how its magnetic environment behaves, and how its moons interact with the enormous planet around them. We can describe structures extending thousands of miles and detect forces operating far beneath visible clouds. Still, when you ask what truly lies inside Jupiter, the most accurate answer remains incomplete. We know more than ever, and somehow there is still more to measure. Earth's history may carry an imprint from a planet we never see from its surface. Jupiter formed more than 4 billion years ago, yet its gravity helped shape the arrangement of material from which Earth eventually emerged. The connection begins with migration. Early Jupiter did not necessarily remain where it formed. As it interacted with the young solar system's disk of gas and dust, gravitational exchanges could have moved the giant planet inward before Saturn altered that path and helped send Jupiter outward again. Those movements rearranged the material available to the growing rocky worlds. Earth, Venus, and Mars developed within a region whose contents had already been disturbed, scattered, and redistributed by larger bodies. Our planet's eventual mass may therefore reflect a history written partly by Jupiter's changing orbit. Water adds another layer. Earth's oceans contain an enormous record of ancient delivery. Some of that water may have arrived through asteroids and other bodies carrying water-rich minerals, while Jupiter's gravity influenced how material moved between the outer and inner solar system. The exact contribution remains debated. We cannot trace individual molecules backward across billions of years. Yet, models of planetary formation consistently show that giant planets can strongly alter the paths of smaller bodies. Jupiter's influence also reaches into Earth's impact history. Its gravity can scatter comets and asteroids, sometimes sending them toward the inner planets, and sometimes ejecting them from the solar system altogether. Whether Jupiter primarily acts as a shield is more complicated than the familiar image suggests. In some situations, Jupiter reduces impacts. In others, its gravity redirects objects inward and increases them. That balance matters for life. Earth has experienced major impacts throughout its history, including events capable of reshaping climate and ecosystems on a global scale. The frequency and distribution of those impacts depended partly on the architecture of the solar system itself, including the gravitational influence of the giant planets. Complex life, therefore, developed within a particular celestial environment, changed the architecture, and the history of evolution could unfold differently. We can take the idea further. When astronomers study planets around other stars, they are beginning to ask whether planetary systems require arrangements resembling our own. A distant giant planet may influence where smaller worlds form, how much material reaches them, and how their orbits evolve. That does not mean every Earth-like world needs a Jupiter. Nature has many ways to build planetary systems, but our own system demonstrates how deeply connected its members can become. Jupiter did not protect Earth deliberately. It did not deliver water with any purpose. Gravity has no intention. Still, over billions of years, countless gravitational encounters produced a planetary arrangement in which Earth became stable enough for oceans, atmospheres, chemistry, and eventually biology to persist. When you look back across that history, Jupiter becomes more than the largest planet. Its influence belongs to the architecture surrounding it. And somewhere within that architecture is the Earth we know. Jupiter has been here longer than every human memory, every city, every language, and every civilization that has watched it cross the night. For roughly 4.5 billion years, its enormous atmosphere has turned, its interior has compressed, and its gravity has shaped the worlds moving around it. Nothing about that persistence requires an audience. The Great Red Spot can rotate for centuries without a witness, while helium descends through layers of metallic hydrogen far below the clouds. Io continues its volcanic activity under gravitational stress, and Jupiter's polar cyclones maintain their strange arrangements according to physical processes we are still learning to describe. Europa carries another kind of uncertainty. Beneath its frozen exterior, an ocean may have remained in contact with rock for geological ages, supplied with energy by Jupiter's relentless gravitational influence. Whether that environment contains biology remains unknown, and no observation has yet crossed that boundary. Humanity, however, has begun sending instruments toward it. Europa Clipper is traveling toward Jupiter, carrying equipment designed to examine Europa from repeated close approaches. Its arrival will not make the moon's ocean visible, but it will sharpen our understanding of what lies beneath the ice. Far beyond Jupiter, Voyager 1 continues its outward passage. Launched in 1977, it encountered Jupiter before traveling onward into interstellar space. Among its instruments is the Golden Record, carrying sounds, music, spoken greetings, and images chosen to represent life on Earth. The spacecraft is now billions of miles from home. Its journey has become a moving record of how far curiosity can travel. Yet Jupiter remains almost impossibly distant from ordinary human experience. We can calculate its gravity, measure its magnetic environment, and study patterns within its atmosphere from instruments sent across hundreds of millions of miles. That distance changes the meaning of observation. Every image is received after a journey through space. Every measurement becomes a small connection between a machine and a world we cannot visit directly. You can look at Jupiter through a telescope and see only a bright disk. Behind that appearance lies an atmosphere thousands of miles deep, an interior compressed into unfamiliar states of matter, and a family of moons shaped by forces operating across immense distances. There is something useful in that scale. Jupiter does not need to be frightening. It does not need to represent anything. It exists as a physical world, governed by gravity, pressure, heat, chemistry, and motion. We are the ones who attach stories to it. And still, the remarkable part is that we can discover those stories at all. A species living on a small, rocky world has built machines capable of crossing the darkness, measuring another planet's atmosphere, listening to its radio emissions, and sending those measurements back home. Jupiter will continue without us. Its storms will turn, its moons will orbit, its interior will slowly evolve. But for a brief moment in cosmic time, we are here to notice.